Okay, our time is up. I think we can get started for today, and then we can always share later on. I would like to hand over to my colleague Oghomwen now to take us through today's session. IG.
Awesome. Welcome again, everyone. So to begin, I think what I'll do is share a video that sort of summarizes everything we talked about yesterday, or maybe not summarize, but give us like a high level overview, really, of what we talked about yesterday. All right, so go ahead and play that video now.
Well, if we come back now to this first picture, being computer science or really problem solving,
is the audio good?
Say we have more than enough.
Yes, we can hear the audio.
Awesome. Just push the quality up. HD.
Enough ways now to represent information, input and output, so long as we all just agree on something. And thankfully, those before us have given us things like ASCII and Unicode, not to mention MP4s, Word documents, and the like. But what's inside of this proverbial black box into which these inputs are going and the outputs are coming, well, that's where we get this term you might have heard too, an algorithm, which is just step-by-step instructions for solving some problem, incarnated in the world of computers by software. When you write software, aka programs, you are implementing one or more algorithms, one or more sets of instructions for solving some problem. And maybe you're using this language or that, but at the end of the day, no matter the language you use, the computer is going to represent what you type using just zeros and ones. So what might be a representative algorithm? Nowadays, you might use your phone quite a bit to make calls or send texts or emails, and therefore you have a whole bunch of contacts in your address book. Nowadays, of course, this is very digital, but whether on iOS or Android or the like, you might have a whole bunch of names, first name and or last, as well as numbers and emails and the like, and you might be in the habit of like scrolling through on your phone all of those names to find the person you want to call. It's probably sorted alphabetically by first name or last name, A through Z, or some other symbol. And this is frankly quite the same as we used to do, back in my day of CS50, when we just used a physical book. In this physical book might be a whole bunch of names alphabetically sorted from left to right, corresponding to a whole bunch of numbers. So suppose that in this old Harvard phone book, we want to search for John Harvard. We might, of course, start quite simply at the beginning here, looking at one page at a time. And this is an algorithm. This is like literally step by step looking for the solution to this problem. In that sense, if John Harvard's in the phone book, is this algorithm, page by page, correct, would you say? Yes. Like if John Harvard's in the phone book, obviously I'm eventually going to get to him. So that's what we mean by correct. Is it efficient? Is it well designed, would you say? No, I mean, this is going to take forever, even just to get to the J's or the H's, depending how this thing's sorted. All right, well, let me go a little faster. I'll start like 2 pages at a time. 2, 4, 6, 8, 10, 12, and so forth. Sounds faster. Is it correct? OK, why is it not correct? Yeah. Exactly. If I start on an odd number of pages and I'm going 2 at a time, I might miss pages in between. And if I therefore conclude when I get to the back of the book there was no John Harvard, I might have just erred. This would be, again, one of these bugs. But if I try a little harder, I feel like there's a solution. We don't have to completely throw out this algorithm. I think we can probably go roughly twice as fast still. But what should we do instead to fix this? Yeah, I'm back.
Google Digital Skills for Africa. They give more than 40 online courses where they're free. You fit learn new.
Nice. So I think what many of us, most of us, if we even use this technology anymore these days, we might go roughly to the middle of the phone book just to kind of get us started. And now I'm looking down. I'm looking for J, assuming first name, J Harvard. And it looks like I'm in the M section. So just to be clear, what should I do next? OK, and presumably it is. John Harvard would be to the left of this. So here's an opportunity to figuratively and literally tear this particular problem in half, throw half of the problem away. It's actually pretty easy if you just do it that way. The hard way is this way. But I've now just decreased the size of this problem really in half. So if I started with like 1,000 pages of phone numbers and names, now I'm down to 500. And already, we haven't found John Harvard, but that's a big bite out of this problem. And I do think it's correct, because if J is to the left of M, of course, he's definitely not going to be over there. And I think if I repeat this, again, dividing and conquering, if you will, here I might have gone a little too far. Now I'm in like the E section. So let me tear the problem in half again, throw another 250 pages away, and again repeat, dividing and conquering until finally, presumably, I end up with just one page of a phone book on which John Harvard's name either is or is not. But because of the algorithm you propose step by step, I know that he's not in anything I discarded. So dramatic as that might have been made out to be, it's actually just harnessing pretty good human intuition. Indeed, this is what programming's all about, too. It's not about learning a completely new world, but really just how to harness intuition and ideas that you might already have and take naturally, but learning how to express them now more succinctly, more precisely, and using things called programming languages. Why is an algorithm like that, if I found John Harvard, better than, ultimately, just doing the first one, or even the second, and maybe doubling back to check those even pages? Well, let's just look at a little chart here. Again, we don't have to get into the nuances of numbers, but if we've got like a chart here, XY plot, on the x-axis here I claim is the size of the problem. So measured in the numbers of pages in the phone book. So the farther you go out here, the more pages are in the phone book. And here we have time to solve on the y-axis. So the higher you go up, the more time it's going to be taking to solve that particular problem. So let's just arbitrarily say that the first algorithm, involving like n pages, might be represented graphically like this. No matter the slope, it's a straight line, because there's presumably a one-to-one relationship between numbers of pages and number of seconds, or number of page turns. Why? If the phone company adds another page next year because some new people move to town, that's going to require one additional page for me, 1-to-1. If, though, we use the second algorithm, flawed though it was, unless we double back a little bit to fix someone being in between, that's too going to be a straight line, but it's going to be a different slope, because now there's a 2-to-1 or a 1-to-2 relationship, because I'm going 2 pages at a time. So if the phone company adds another page, that's going to take me only, or another 2 pages, that's still only just one more step. And you can see the difference if I kind of draw this. If this is the phone book in question, this number of pages, it might take this many seconds on the yellow line to represent or to solve, to find someone like John Harvard. But of course, on the first algorithm, the red line, it's literally going to take twice as many steps. And what do the n's here mean? N is the go-to variable for computer scientist or programmer, just generically representing a number. So if the number of pages in the phone book is n, the number of steps the second algorithm would have taken would be, in the worst case, n over 2. Half as many, because you're going twice as fast. But the third algorithm, actually, if you recall, your logarithms looks a little something like this. There's a fundamentally different relationship between the size of the problem and the amount of time required to solve it that technically is log-based to of n, but it's really the shape that's different. And the implication there is that if, for instance, Cambridge and Alston, 2 different towns here in Massachusetts, merge next year, and there's just one phone book that's twice as big, no big deal for that third and final algorithm. Why? You just tear the problem one more time in half, taking one more byte. That's it. Not another 1,000 bytes just to get to the solution. And put another way, you could walk out way, way, way out here to a much bigger phone book, and ultimately, that green line is barely going to have budged. So this then is just a way of now formalizing and thinking about what the performance or quality of these algorithms might be. And before we now make one more formalization of the algorithm itself, any questions then on this notion of efficiency or now performance of ideas? Yeah. A lot of phone books over the years, and if you or your parents have any more still somewhere, we could definitely use them because they're hard to find. Other questions? But thanks. Other questions here too? No. Oh, was that a murmur? Yes, over here. Sorry, say again? Oh, yeah. Hopefully, and then we could then we'd have a little something more to use here. So now if we want to formalize further what it is we just did, we can go ahead and introduce this, a form of code, aka pseudocode. Pseudocode is not a specific language. It's not like something we're about to start coding in. It's just a way of expressing yourself in English or any human language succinctly, correctly, toward an end of getting your idea for an algorithm across. So for instance, here might be how we could formalize the code, the pseudocode for that same algorithm. Step 1 was pick up the phone book, as I did. Step 2 might be open to the middle of the phone book, as you proposed that we do first. Step 3 was probably to look down at the page, as I did. And step 4 gets a little more interesting, because I had to quickly make a decision and ask myself a question. If person is on page, then I should probably just go ahead and call that person. But that probably wasn't the case, at least for John Harvard. And I opened to the M section. And so there's this other question I should now ask. Else, if the person is earlier in the book, then I should tear the problem in half as I did, but go left, so to speak. And then not just open to the middle of the left half of the book, but really just go back to step 3. Repeat myself. Why? Because I can just repeat what I just did, but with a smaller problem, having taken this big bite. But if the person was later in the book, as might have happened with a different person than John Harvard, then I should open to the middle of the right half of the book, again go back to line 3. But again, I'm not going to get stuck doing something forever like this, because I keep shrinking the size of the problem. Lastly, the only possible scenario that's left, if John Harvard is not on the page, and he's not to the left, and he's not to the right, what should our conclusion be? He's not there. He's not listed. And so we need to quit in some other form. Now, as an aside, it's kind of deliberate that I buried that last question at the end, because this is what happens all too often in programming, whether you're new at it or professional, just not considering all possible cases, corner cases, if you will, that might not happen that often. But if you don't anticipate them in your own code, pseudocode or otherwise, this is when and why programs might crash. Or you might see stupid little spinning beach balls or hourglasses, or your computer might reboot. Why? It's doing something sort of unpredictable if a human, maybe myself, didn't anticipate this. Like, what does this program do if John Harvard's not in the phone book? If I had omitted lines 12 and 13, I don't know. Maybe it would behave differently on a Mac or PC, because it's sort of undefined behavior. And these are the kinds of omissions that, frankly, you're invariably going to make. Bugs you're going to introduce, mistakes you're going to make early on, and me too, 25 years later. But you'll get better at thinking about those corner cases and handling anything that can possibly go wrong. And as a result, your code will be all the better for it. Now, the problem ultimately with learning how to program, especially if you've never had experience, or even if you do, but you learned one language only, is that they all look a little cryptic at first glance. But they do share certain commonalities. And in fact, we'll use this pseudocode to define those first. Highlighted in yellow here are what henceforth we're going to start calling functions. Lots of different programming languages exist, but most of them have what we might call functions, which are actions or verbs that solve some smaller problem. That is to say, you might use a whole bunch of functions to solve a bigger problem, because each function tends to do something very specific or precise. These then, in English, might be translated in code, actual computer code, to these things called functions. Highlighted in yellow now are what we might call conditionals. Conditionals are things that you do conditionally based on the answer to some question. You can think of them kind of like forks in the road. You go left or go right or some other direction based on the answer to some. Now in yellow are what we would call Boolean expressions, named after a mathematician, last name Boole, that simply have yes/no answers. Or if you prefer, true or false answers. Or heck, if you prefer, 1 or 0 answers. We just need to distinguish one scenario from another. The last thing manifest in this pseudocode is what I might highlight now and call loops. Some kind of cycle, some kind of directive that tells us to do something again and again, so that I don't need a 1,000-line program to search a 1,000-page phone book. I can get away with a 13-line program, but sort of repeat myself inherently in order to solve some problem until I get to that last step. So this then is what we might call pseudocode. And indeed, there are other characteristics of programs that we'll touch on before long, things like arguments and return values, variables, and more. But unfortunately, in most languages, including some we will very deliberately use in this class and that everyone in the world these days still uses, is programs tend to look like this. This, for instance, is a
All right. Anyone has any questions from the video? You can use the Q&A or chat or just raise up your hand and then probably unmute your mic and you speak. All right, so that's like a recap or like a very short summary of what we really did look at yesterday. We went more into analyzing the performance of algorithms using the worst case scenario, which is typically represented by big O notations. All right, and I did promise to show, somebody did ask yesterday if the size of or the time it takes for an algorithm to solve a problem is if it correlates with the space complexity also of the algorithm, and I said that's not always the case. There's really no correlation there, and I was going to show an example between bubble sort and merge sort. I'll show that in a second, but then I want to give some time for anyone with any questions at this point. Otherwise, I can just go ahead and show that already. All right, cool. So far, so good. No questions. Okay, I can't remember who exactly was asking yesterday about the correlation between space complexity and time complexity, but the classic example I can use to demonstrate that is something called there's two algorithms for sorting elements within a collection. All right, and one of them is bubble sort, and one of them is merge sort. So I'm going to do bubble sort on the left and just show you what it looks like. Say we have an array with 4 elements. Please confirm you can still hear me. I thought I saw a raised hand. Okay. Was it Oluwatu missing? I thought I saw a raised hand. Do you want to ask something? All right, no question there. Okay, so all right, so say we have an array on the left. I'll show you what's called bubble sorts. Right? We have an array with 4 elements, for example, 4, 3, 2, 1. How bubble sort works is it compares 2 values, and if the lower value is on the right, it moves it to the left, and then moves the value on the left to the right. And so quickly sorting this array using bubble sort, the next iteration through this array for bubble sort will look something like this. Will look like 3, 4. It then compares 3 and 4. 3 comes to the first box, 4 comes to the right. It then compares 2 and 4. 2 comes forward, 4 goes to the right. It then compares 1 and 4. 4 goes backwards to the right. 1 comes to the left. And so at first pass, you'd have this. At second pass for bubble sort, you have 3 and 2 comparison. 3 goes to the right, 2 comes forward. 1 is lower, so compare 3 and 1. 1 comes to the left, 3 goes to the right. Compare 3 and 4 now. 3 stays in this position because 3 is smaller than 4 and 4 stays in that position. By the third iteration, you have the comparison between 1 and 2. So 1 comes forward, 2 moves to the right, 2 and 3, 3 stays on the right, 3 and 4, 4 stays in the position. The bubble sort does one final pass to confirm that everything is in the place where they should be. So it does another comparison All right, and that's it really. So in terms of time complexity, right, for this, now let's see how many steps we had to do. Because we had n, we had to do n comparisons in the first pass, so we had to do 4 comparisons here. The next pass, sorry, we had to do 3, 2, 4 and 3, 3 and 2, 2 and 1. So we have to do 3 comparisons. In any case, on each layer, we have to do 3 comparisons. But then we have to touch each element within the array. So there were 4 elements. So ideally, that's n. So 4 elements here. We compared 4 elements here, and we compared 4 elements here. And you notice that on each layer we have 4 elements, but then the entire stack or depth in terms of the solution is also 4. And the size of the array node is also 4, right? And so n is equal to 4. And so this algorithm takes 4 times the depth and 4 times the comparison. So that's n times in terms of the comparison on one level, n times, and then the comparison in terms of depth is also n. So this algorithm takes n squared time, right? But in terms of space complexity, so the big O of this is n squared. And in terms of space complexity, notice that we did not need any extra space while doing the comparisons, right? And so ideally, because we did not need extra space, the space complexity, let me just put T for time here. Space complexity for this would be n, because we still use the original array, which had a size of 4, to do the comparisons for this algorithm. Now compare that to something called a merge sort on the right. So I just hope I have enough space to represent the merge sort. Yeah. So same array. Sorry. Put in 4 here, 3, 2, or 1. So what merge sort essentially does is it divides the array, very similar to the phone book example we saw in the video. It divides the array until the array can no longer be divisible. And then it then composes back an array, placing each element in the position where they should be. So what merge sort to do on another in the first iteration would be to divide an array with 4 elements into 2 different arrays. To break this down to 4 and 3, and then break this down to 2 and 1. So now the merge sort has divided the 4-element array into 2 sub 2-element arrays. And typically, you would agree that an array of size 2 is easier to sort than an array of size 4. So what this problem has done is it has broken down, what this sorting algorithm rather has done is that it has broken down the problem into 2 smaller pieces so you can solve it. But then again, at the 3rd pass, what it does is breaks down each of the elements into 2 arrays. Each of the first 2 that it broke down, it now breaks down those arrays again into a further 2 sets of array for each side. So you have 2 sets of array on this side, 4 and 3. On this side, you have 2 and 1. But I ideally should not put them on the same level because that's not how it does it. Or maybe I can. Let's just leave it on the same level. So at this point, we have 4 arrays with 1 element each. And then we can no longer divide any on any side. Yeah, we can no longer divide on any side. And so what we then do is we now start to compose back the array. So it then says the next step for the merge sort is to compose the array in such a way that the array is already sorted. So notice we went from from two sets of arrays to one value each on each side. So we're going back to the top level, the level immediately above it, and composing the array back to size of 2. So between 4 and 3, 3 is smaller, so we put 3 first and put 4 here. And for 1 and 2, 1 is smaller, so we'll put 1 here and 2 here. So now I've gone back to this, right? And then next is compose these two individual arrays back to our 4 arrays, our array of size 4 rather. So what we then have is create another array and then add all the values from the top from those individual arrays in a sorted order. So we now have 1, 2, 3, and 4. And that's merge sort. But notice that this merge sort has done this whole sorting in only 2 steps. 1 step and the second step. But in terms of space complexity, notice that it has used more arrays in solving the problem. So it has 2 arrays on this layer and 4 arrays on this layer. And then it composes it back using 2 different arrays on this layer and then 1 array eventually on the last layer. And so that's more space in memory that it's using than bubble sort, which uses no extra space in memory. And so even if the merge sort on its own uses the original space for the array to represent this last merging, it still uses new sets of arrays on this layer here, this layer here, and this layer here. All right, so it has used more space, but it's definitely more efficient because it has solved it in 2 steps. So we can then say for this, the algorithm performance in terms of time really is big O of log n. Reason is that if I double the size of this array, the original array, it will take me only 1 extra step to sort it. If I quadruple the size of the array, it will take me only 1 extra step to also sort it from the previous double size. And so with the doubling of the size of the problem, it really only takes me 1 extra operation to eventually sort the whole thing. And so the performance is log n, which is way better than n squared on this side. And here we would say we're using the original space, which was 4 here, and then we're using again 4 new spaces here. But then this is 2. Sorry, 2 times 4. 2 arrays with 4 values here. This is new. And then we're using 1 times 4 values. Yeah. And then here again, we're using 2 times 4. And here we're using 4. So if we add that up, that's 4 plus 2 times 4, which is 8. That's 4 plus 8 is 12. This is I mean, if we're counting bytes, this isn't exactly accurate. Yeah. So, but I mean, I'm counting in terms of elements. So 4 plus 2 times 4, which is 8, which that's 12. 1 times 4, which is 4, that's 16. Plus also 2 times 4, which is 8. 24 plus 4, that's 28. So I could say, I mean, this is 28, which is 28 divided by 4. That gives us 5. 4 times 5 is 20. 4 times 6, 24. 4 times 7, 28. So that's in this case it is more than n. So we will have 7n for this particular value, but in terms of representing it as a formula, that would be where n is 4 raised to power 2 is 16. That's more than n. That's even more than 2n rather. Or 2 raised to power n, which is 4. 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. That's something around 2n, slightly more. But this, I mean, this is not accurate. I'm just giving an approximation anyway. Yeah. And then someone is asking, what if the size of the array is an even number like 5? So let's try to solve that. All right, say you have an array that's an even number 5. Yeah. Let's see how the merge sort does that. All right. So our array has an array is something like this. 5, 4, 3, 2, 1. So if we take the size of the array to be 5, 5 divided by 2 gives you what? An integer number that will give you 2. So what the merge sort does is that it knows that there's one value left. For uneven numbers, it sees that there's one value left. So typically the last element would be the one left. And so you have two arrays of 4, 5 and 4, 3 and 2, and they have one array of 1. But it can no longer split this. So it will still bring this down and then split all the others. So 3, 2, 5, 4. Or rather, no, I think that's not what happened. Apologies. It will have something like this, or rather, it will have 5, 4, 3. In practice, it will be like this: 5, 4, 3, 2, and 1, because it knows that the summation of half each, because 2 plus 2 doesn't sum up to 4. It doesn't sum up to 5 rather. It knows that there's one element missing, so it just adds that one to either sides of the new array is creating. So you can either add it to here or add it here. So one of the array has 3. So when it comes to the next level, it's going to split each. So you have another array here. So you don't have this because 3 over 2 is 1, but then one array stands out. So you have 5, 5, 4. You then have 3 here. And then you have 2 and 1. So you have on the next level, and then at the bottom level, you notice you are going to only split this to 5 and 4. And then what you do is merge 5 and 4 again. Then you bring these other layers on the next merge. So you ideally should have should then have 1 come here, 2 go here, 3, 4, and 5. That's what happens. And because we use a recursive call for a merge sort, you have the condition to break when the array size becomes 1, right? And so what will happen is at this point in the call, the right side of the array stops breaking into smaller arrays because it can no longer be divisible. But the left half of the array still continues to go through the function, and then eventually it returns because it's a stack call. Eventually it will return back to this level and then be merged back to this level eventually. Right, so I hope that answers your question. This is slightly a high-level explanation. I mean, I wish I could show you how it's done in code. I've written merge sort once, but I mean, I don't know where I put the code, so I can't exactly access it at the moment. I'll show you how it works or how it looks like in code, really. Well, I can show you the pseudocode for merge sorts. Yeah, I mean, the pseudocode is already, I mean, you should already get it. And so there's really no need to show you what the pseudocode looks like. Right, Alan, does that answer? I mean, I could show a video of merge sorts that sort of explains it, but I'm not sure if they do talk about, or if they do explain when the value is uneven. I have a video here for merge sorts. Maybe we'll see some of it. Let me just play this.
Simplest we've seen thus far, but deceptively simple. The pseudocode for merge sort, quite simply, is this. Sort the left half of numbers, sort the right half of numbers, merge the sorted halves. And notice, even at first glance, this feels kind of unfair. Like, here's an algorithm for sorting, and yet I'm literally using the word sort in my algorithm for sorting. It's like in English, if you're asked to define a word and you literally use the word in the definition, like that rarely flies, because you're just sort of making a circular argument. But in code, it's OK so long as there's one special step that's doing something a little differently, and so long as the problem keeps getting smaller and smaller. And indeed it is. This pseudocode is not saying sort the numbers, sort the numbers, sort the numbers. No, it's dividing the problem in half and then solving the other half as well. So it's shrinking the problem on each iteration. Now, I will disclaim, we're going to need that so-called base case again. I'm going to have to do something stupid but necessary and say, if there's only one number, quit. It's sorted. That's the so-called base case. The recursive case is where the function calls itself. But this is indeed our third and final sorting algorithm called merge sort. And we'll focus here really on the juiciest pieces. One, this notion of merging. So in fact, Brian, can we cut over to you just so we can define, before we look at the merge sort algorithm itself, what do we even mean when we say merge sorted halves? So for instance, Brian has on his shelf here 2 arrays of size 4. In the first array on the left are 4 integers, 3, 5, 6, 8. And in the right side, in another array of size 4, are 4 numbers too, 1, 2, 4, 7. Notice both the left is sorted and the right is sorted. But now, Brian, I would like you to merge these sorted halves. Tell us what that means.
Sure. So if I have a left half that's sorted from smallest to largest, and I have a right half that's also sorted from smallest to largest, I want to merge them into a new list that has all of the same numbers, also from smallest to largest. And I guess where I could start here is that the smallest number of the combined array needs to begin with either the smallest number of the left half or the smallest number of the right half. Because on the left, the smallest number is the 3, and on the right, the smallest number is the 1. One of those two has got to be the smallest number for the entire array. And between the 3 and the 1 is smaller. So I would take that 1, and that's going to be the first number, the smallest number of the merged two halves. And then I guess I would repeat the process again. On the left side, the smallest number is the 3. On the right side, the smallest number is the 2. Between the 3 and the 2 is smaller. So I would take the 2, and that's going to be the next number. So I'm slowly building up this sorted array that is the result of combining these two. Now I'm comparing the 3 on the left to the 4 on the right. Between the 3 and the 4 is smaller. So I'll take the 3, and we'll put that one into position. Now I'm comparing the 5 on the left with the 4 on the right. Between the 5 and the 4 is smaller. So that one goes into position. And now I'm comparing the 5 on the left with the 7 on the right. The 5 is smaller, so the 5 goes next. Next, I'm comparing the 6 on the left with the 7 on the right. The 6 is still smaller, so that one is going to go next. Now I'm comparing the 8 and the 7, the only two numbers left. The 7 is the smaller between the two, so I'll take the 7 and put that into place. And now I'm only left with one number that hasn't been put into the merging of the two halves, and that's the number 8. So that number is going to take up the final position. And now I've taken these two halves, each of which was originally sorted, and made one complete array that has all of those numbers in sorted order.
Indeed, and consider what we've done. We've essentially verbally and physically kind of defined a helper function, our own custom function, if you will, whereby Brian has defined what does it mean to merge two arrays, specifically merge two sorted arrays. Because why? Well, that's a building block that I think we're going to want in this merge sort algorithm. So just like in actual C code, you might have defined a function that does some small task. So have we now verbally and physically defined the notion of merging. The mind-bending part here is that sort left half of numbers and sort right half of numbers is kind of already implemented. There's nothing more for Brian or me to define. All that remains is for us to execute this algorithm, focusing especially on these 3 highlighted lines of code. And let me disclaim that of the algorithms we've looked at thus far, odds are this will be the one that doesn't really sink in as quickly as the others. Even if the others might have taken you a moment, a day, a week to settle in, or maybe you're still not quite there yet, that's fine. Merge sort is a bit of a mind-bending one because it seems to sort of work magically. But it really just works more intelligently. And you'll begin to get more comfortable with harnessing these kinds of primitives so that we can ultimately, indeed, solve problems more efficiently. So Brian has kindly put the numbers again on the top shelf, and he has put them into their original unsorted order, just like for selection sort and bubble sort. And Brian, I'd like to propose now that we execute this merge sort algorithm. And if you don't mind, I'll recite aloud at first the few steps. So here is one array of size 8 with unsorted numbers. The goal is to sort these numbers using merge sort. And recall that merge sort essentially is just 3 steps.
Who asked this question? Alan, this really doesn't answer your question in terms of if, but in principle, that's what happens. The last value typically goes into a subarray. So one array is always going to be bigger than the other. I saw a raised hand. Yeah. Did you want to ask something? Any questions so far? Anyone? No questions? All right, but I mean, it's already representative on the screen how merge sort definitely uses more memory because it typically needs a another section in memory to do all of the sorting and merging that it does. However, bubble sort is typically just done within the same space in memory that is already allocated to the original array. All right. So I think the next thing we'll look at, I also promised someone that we would look at the performance of a couple of data structures in terms of their big O notations of their associated operations, right? And so I would talk about this and also try to explain how the big O notations, I mean, the worst case for the operations on these data structures came about, right? So for arrays, the worst case to access something within an array is big O of 1. It always takes one step to access a value within an array. And to show how that is, let me draw something. So we originally said that an array is a data structure that has or that's implemented and allocates itself continuous space in memory. So typically, say this is our array in memory. The array would start at a certain position within memory. Say, for example, say the starting position we get is 35, and we allocate after that 35th position within memory. We allocate 1, 2, 3, 4, 5 continuous spaces to an array. So this array is of size 5. And we have a value in the array 1, 2, 3, 4, 5, right? And because of the way we number in computer science, the positions are 0, 1, 2, 3, and 4, right? And so what 0 typically points to is this memory, or this location in memory, which is 35. This is the location, let's say this is the location in actual memory, right? And these are the indexes. If I was to get the number 5 from within this array, all I need to do really is specify array position 4, right, in my program. And what happens under the hood is that the runtime goes to the array and gets the first position, and it sees that the first position in memory is 35, right? And then it knows that because the position you're trying to get is the 4th position, which is, of course, because it's, I mean, the 4th index rather, but it's the 5th position. What happens then is that it adds 4 in this case. So it adds 4, right, to the 0th index. So it becomes 35 plus 1, 35 plus 1. This position is 35 plus 1. This other position is 35 plus 2. Right? Eventually, this is 35 plus 4. So everybody gets the gist up to this point. Any questions? All right. So in any case, what then happens is it takes this 4th index that you have specified, just adds that index to the address of this first one, and then that allows it to jump directly to this position. So it doesn't have to then go through 0, 1, 2, 3, 4. Just adds 4 to the first element or to the first index, and then it can jump to the value at the 4th index within the array. So that's why accessing an element in the worst case from an array takes one step really, because this is what happens. Add the index to the first position, and then that gives you the address, and then you just jump straight to the address. All right, any questions? All right, no questions in the Q&A, no questions in the chat. Is everything clear so far? Anyone not understanding anything? All right, everybody seems to be following, which is awesome. Please ask me questions. I mean, today is really about questions and answers, just generally looking at stuff that you maybe have questions you maybe have from yesterday, or things that weren't clear to you. Today is the day to clarify everything, really. All right, so let's look at the next one, which is searching, right? So if I needed to search in an array, again, let me just erase this. Right. So I have an array like this. Undo. So I have this array. There's 4 here. There's 3. There's 1. There's 2. And then I had to look for the value 2. What will happen is I will typically start from the first index. Check, is the value 2 here? That's no. The value 2 in the next index? No. Is the value 2 in the next index after that? No. Is the value 2 in the last index? Yes. And so you see that because I needed to search through the array and find the value, I typically would have taken n number of steps, because the size of the array size is 3. Number of steps it took me to search for the value 2 within the array was, array size is 4. Number of steps it took me to find the value 2 within the array was big O of 4, which translates to big O of n, because n is 4. So that's how searching through an array works. All right, Dennis asks, so is there a language that is good for solving DS questions? Can someone use JS2 as a language? Yeah, ideally, every language has like an implementation for, I shouldn't say every language, because I haven't used every language that's out there. But most languages have an implementation for the usual or for the most popular data structures. And so you should ideally be able to use any language to solve any data structure question. Otherwise, you can implement the data structure yourself for languages that do not already have the data structure. You can implement the data structure as a library and then use it within your code. That'd be interesting. I'd love to see some people implement data structures. I think a linked list is pretty easy to implement. So someone can try their hands on that. All right. So let's look at the next one. So to insert a value in an array, typically also takes n steps. Here we have, looking at this array, the array already on the screen, it has 4, 3, 2, 1 as elements. Say I now want to insert a new value at the end of the array, at the beginning of the array rather. or I'll just use a new array since this might not exactly explain insertion. Right, so let me erase this. Erase that. All right, so I have an array, for example, with 5 spaces. There's values 1, 2, 3, 4, 5, or rather the array has six spaces, right? Say I needed to insert, or let me just also specify their index is 0, 1, 2, 3, 4, 5. If I need to insert an element in the 0th index of this array, what I'll need to do is move over each element that already exists in the array. So what will happen is this same array becomes, say I needed to insert the number 6 at the first index. So what will happen is the new array becomes 5, 4, 3, 2, 1, 6. The indexes are 0, 1, 2, 3, 4, 5. So because I needed to insert an array or insert a value into an array, which had 5 elements originally, I had to move all the 5 elements over. I had to shift them one after another just so I could insert one single value at the first index. And so that took me n number of steps because there were n elements within the array, which is in this case n equal to 5. And then I had to move over 5 of all those values, or all of them entirely, to the right or to the left, depending on what you needed or how you needed to insert the value. So in the worst case, it will take you n number of steps to actually insert a value into an array. Right. And then also to delete an array, which is kind of like the reverse. If I needed to delete the 6, what will happen is I will then also shift it's 1, 2, 3, 4, 5. I'll then also shift all the values. This is 0th index, 1, 2, 3, 4, 5. This was the insert operation that took us n steps. Here we're deleting. All right. So to delete the value at the 0th index, which is 6, I'll have to move all the other values back to the left. And that would have taken me n number of steps to also do that. N being that I'll delete the first element, remove the first element out of that position, and move over the element at the index 1, move everything over one after another to the left, and then there I would have had a deletion. And so that's n steps altogether. All right. For a stack, let me just erase this. So for a stack, to access an at the worst case 6n. Let's look at a stack with 5 elements. So 1, 2, 3, 4, 5. For a stack, we know that stack is a last first in, last out, or last in, first in, last out data structure, which is also a last in, first out data structures before. All right, so on the stack, this is the 5th, this is the 4th, elements. This is the third. This is the second. This is the first. Now, if I were to access the element 1, the first element, I'll then have to move all these other elements out first before I can access this. And so it will take me n steps at the worst case to access elements within a stack. For searching, it's pretty much the same. If I were to check the values in each element within the stack, I would have to do n number of steps also. And then if I were to insert into a stack, all I need to do is drop something else on top. That becomes the 6th element, because the stack only has one direction in terms of adding. So the insertion operation for a stack is big O of 1. It's constant time. It never changes. And then also to delete an element from a stack is also big O of 1, because all I need to do is pop the element, the 6th element, and then I would have deleted it. So that's also constant time. All right. And so it's very also similar for a queue. For a queue, to access an element, a queue being this is stack. A queue being the first in, first out data structure. So I have 1, 2, 3, 4, 5 elements. The first one in should be first one out. I have 1, 2, 3, 4, 5. Or I think the numbering should be the other way around. So this is the first one in. So now I'll draw something on these edges just to show the direction. So first one into the queue is also the first one out of the queue. Now, how long would it take us to access elements within the queue? Right, so if I added something from the back of the queue, to access that thing, I'll have to move everything at the front of that element out before I'll then have access to the last thing that I added. And so that would take n steps. So that's for access, big O of n. Also for searching, very similar. If I needed to compare values within each, or the values of the elements within the queue, say the last item added to the queue, and I've had to remove everything in front of that item to reach that element and compare the value. So that's also n. To insert into a queue is also one step. Always you have to insert from the back of the queue, and so all you need to do is enqueue. It's one step to enqueue, constant time. To delete is one step to dequeue, because you always remove stuff from the front of the queue, and so that's also constant time. All right, so far so good. Any questions? All right, no questions just yet. So now let's look at the linked list. Just going to erase all of this. For linked list is quite interesting to analyze the performance of the operations on a linked list. So remember what a linked list originally looks like. So we have a node, for example. The first node, which is the head, typically would have, let's use the 0, which is the first node. It would have, or rather, let's put the number out here, 0. It would have a value, say 2 in the list, and then it will have a link to the next node. So say this node which is in position 1, has a value 4. At this point, it will have a link to the next node. So that's ideally what a linked list is. Say this node has a value 6. The third node, it will then have a link to another node. All right, and then if it doesn't have a link to another node, it ideally is the last node within the linked list. And so this link, the position for the link is null at this point. So that essentially is a linked list. Yeah. So let's now see. At the worst case, for a singly linked list, at worst case, to access an element takes big O of n, because if I were to get the second element for the list, I'd have to start from the head, check the element here. If it's not what I want, I'll have to jump to the next, check the element. If it's not what I want, I then have to jump all that way. And you'll notice that it took me n number of steps to get to the nth value within the linked list. That's for access. All right, for searching, it's pretty much the same. To compare values of the elements within the collection, we also have to do operations that typically will take big O of n. All right, and then to insert, it's pretty sweet. It takes only one step to insert stuff into a linked list. Now, there are two ways to insert stuff in a linked list. You can either insert stuff at the end of the linked list. In this case, what would happen is all you need to do is go to the end of the list and then create a new link to another node. Say the third node, just add a value. Let's put 1 here, and then this becomes null, right? This is one way to insert stuff into a linked list. However, if you needed to insert stuff in the middle of the list, right? This is where I would now say the indexes don't really count. If you need to insert stuff in the middle of the list, you could do something different, which is, well, you typically would do something different. So which is that you can insert another node in the middle. All you need to do is erase the link from 1, create a new node. So you create a new node here, put the value in the node, say 5, link from this node to the new node, and then add the link from that new node to the node that the previous node used to link to. And so you'd have added or inserted an element right in the middle of the linked list. So it's pretty straightforward and easy. Yeah, so the indexes do not, in this case, I was just using the index to you know, represent the positions, but in the implementation of a linked list, there really are no indexes, although some programming languages would allow you access elements within the linked list using indexes. What then happens is that typically would do or take that index you insert and use that as the number of steps to go down the linked list. So they will go down. So the start at the first node, say you specify, for example, you have a list, and then you specify the third index. What will happen is your programming language will go to the first node, take the link from the first node, and go to the second node, take the link from the second node, and go to the third node. So just those three or three movements like within the list. and gets you the element at the third node, really. So it ideally is not an index, it's just a count of how many nodes your program should count before it gives you a value. So it's not an index like you'd typically use in an array. All right. What else have we not looked at? So to insert and to delete, ideally also the same thing. So if I were to delete this node, all I needed to do really is let me erase this first. So if I were to delete this node here, all I need to do is erase this link from here. Also erase this link from here to here, right? And this node becomes free on its own, and then move the link back from here to here. And then I'll have deleted that element. So it really takes one step to unlink one node from two other nodes and then link those two other nodes back together. All right. So any questions so far, so good? Anyone that has anything they'd like to ask at this moment? Right, it seems like everyone understands everything. Yeah, so for next steps, since this has been extremely interesting, I think some of us would like to do like a deep dive into all of this. Like I said from at the beginning of this, it really isn't a boot camp in the sense that boot camps are short, very intensive, and what's the third word? And then they're also very rigorous, yeah. But this isn't very rigorous, short, doesn't go too deep, so it's kind of like a way to really boot you in the sense of starting a computer, right? So you do beat a computer to start. So it's like this is to get you started into a journey of going deep into understanding data structures more, and even algorithms, and how to match those two concepts to really create very powerful applications, right? And so a course I had already recommended earlier, which I'd also recommend, or a couple of courses, CS50 being the number one of them. So everyone, I'll put the link in the chat. Just go ahead and check out CS50. It's an amazing course from Harvard University. Just search that. Introduction to Computer Science and Programming. Takes a deep dive into algorithms and also some data structures. Teaches you a programming language also. So yeah, leaving this link right here. Everyone, check out this course. Also, if you're up to it, yeah, take some courses in mathematics for computer science. They really help you understand some mathematical concepts. Put that link in the course also. This one is from MIT OpenCourseware rather. Check out this course, Mathematics for Computer Science. It's a very sweet and interesting course to take. It might be difficult at first, but if you do some really good research, check out some materials, some support materials, everything is there in terms of notes, text to check out. I think they even have slides. Just dig into those materials. everything will be very clear to you eventually. So I think I also had mentioned that if you have any questions, you can also do a follow-up question or shoot me an email at this email address. Yeah, just to ask follow-up questions. Okay. Yeah. And then, if there's generally anything else or suggestions for new bootcamp topics that you'd like, just something you really like to understand, some new some computer science concepts, not necessarily new, that you really like to get into, please propose also, and then just let us know. I'll get on it. All right. I hope this has been super wonderful for everyone. I hope everyone got a lot out of it, and then uh, ultimately, I hope everyone is able to just go on and get into this stuff more and more, just to really understand it and become a better software engineer. Right? And I look forward to seeing what we all do with all of this knowledge in the future. All right. So I would say thank you, everyone. See you tomorrow. We'll have a general session where we'll just entertain questions. Really, nothing heavy. Not no no. There'll be no presentation really, or all we will do is answer questions from that would have arisen from Monday till today. So if you have any questions, just note them down. Any questions you haven't asked, say from browsing all the resources that were made available earlier, and also from the earlier sessions, just put all together, and then in tomorrow's session, we'll ask and answer everything. So with that being said, I would say thank you all for joining today. Again, I can't wait to see everything we build, after gaining all of this knowledge. Awesome. So thank you, everyone. Have a lovely rest of the day. Bye. See you all.